So welcome back.
Yeah.
Hello. Yes. Hello, Gabriel.
We haven't done the
Yeah, you know
handshake in a
why?
while.
Yes, true. That's true.
For good reason.
Right.
So today is the final episode of Going Native.
Oh no.
Yeah, the final episode of Going Native.
I don't believe it.
Half kidding. So this is the episode where we respond to Nico159's comment feature episode request from a couple episodes back on how to take advantage of the final keyword introduced in C++11. This video is a bit more of the, I guess, the lecture style of the Going Native episodes we have. So hope you guys, find it at a minimum informative and hopefully enjoyable as well. We talked to Patrick.
Yes.
I'm not going to attempt to butcher his last name. I'll let him tell you guys what it is in the video. So
It's pretty long last name.
pretty
I
nice.
agree. I wouldn't try that either. That's good.
So,
okay, let's go see it.
Let's get to it.
Hi everyone, welcome to our latest episode of Channel 9 Going Native. My name is Gabriel Ha, behind the camera, and I'm here with Patrick. Patrick, tell us a little bit about your time here at Microsoft.
Hi, my name is Patrick Satyanathan, and I have been working at Microsoft for the past 8 years, primarily in the area of code generation and optimizations. I have a PhD in computer science, and my graduate studies focused on the area of program analysis and optimization, so this job is sort of a perfect fit for me. When I joined Microsoft, I was working in the Phoenix team. Phoenix was supposed to be a C++ framework intended for doing code generation and optimizations, and it was supposed to unify all the scattered efforts in this area around within the company itself. It eventually moved to incubation, and most of the staff, including myself, were moved to the production compiler, that is the VC++ compiler team. And I have been here since then. I work here primarily in the area of whole program optimization, analysis and optimizations. This happens in the compiler when you specify the /GL optimizations, which triggers what is called link time code generation, or LTCG. In this mode, the compiler packages front-end IL into COF object files, and these don't really contain machine code, but they contain the front-end IL. And when the linker is asked to link one or more of such object files, it turns around and calls the backend to do code generation for these anonymous object files. In this mode, the backend has visibility to the entire program, and it is able to do analysis across functions, across modules, and it is able to use the information gathered from this analysis for doing optimizations. In recent releases of the compiler, I have implemented optimizations like dead catch handler removal and the redundant query interface removal for C++ CLI.
Very nice. Well, I believe our viewers have been briefed on what we'll be talking about today, so let's get right to it.
So the final specifier in C++ was introduced in C++ 11, and to be correct, it is not a keyword really, but it's more of a specifier. The word final itself can be used in two specific contexts where it has specific semantics. In other contexts, it can be used as an identifier, for instance, as a variable name or as a function name. There is no restriction on that. As I mentioned, there are two contexts in which the final specifier can be used. The first context is when you are defining a derived class which has other base classes, and if you specify the final keyword in the class definition, the semantics is that you are prohibiting any other user from deriving from that class. So basically what you're saying is this class is a leaf in the class hierarchy, and it makes no sense to further derive from it and specialize its behavior. So if you declare a class as final and you try to use it as a base class of another class, that is an error, and the compiler will emit an error, and it will fail to compile your program. So typical uses of this would be, let's say you're a library developer, you've designed a nice class hierarchy, and you have some concrete classes at the leaves of your hierarchy, that's at the bottom of your class hierarchy. If you want to prohibit users of your library from further deriving from those classes, then you would make those classes final. So this specifying it as final would prohibit anybody from using such a class as a base class. So now I'm going to show you a simple example of how to use this final specifier to declare a class as final. Here we have, for this example, I've shown a simple class hierarchy with 3 classes. Let's imagine you're developing a library of geometric shapes for a graphic system, let's say a 2D graphic system. You want to have shapes of different kinds, and you want each of those shapes, for example, to draw itself on a 2D screen. Here we have the classes in the hierarchy. I've defined shape as the base of the hierarchy. All it has as data member is a location member, and it has 2 virtual functions. One is draw and the other is scale. The intent is, okay, the draw method will be called on an object of a specific subclass, and it should draw itself on the screen. So I've declared these as pure virtual functions, you will notice. Using this syntax equal to 0, and both the virtual functions are pure virtual functions, which means the shape class is an abstract class, which means it cannot be instantiated. Now I have 2 subclasses derived from the shape class. One I've called a rectangle, which derives from shape, has additional data members, and has some implementation for the draw and scale methods. And the other subclass is a circle, which is also derives from shape, has a radius member, and has its own definitions of the virtual functions draw and scale. Now, for some reason, I've decided that circle is a leaf in the class hierarchy, and nobody should be allowed to further specialize it. You could imagine that rectangle could be specialized in to implement a square in which the width and the height are equal, for instance. And I have decided that no other shape can be specialized from the circle class. And the way I can enforce this in the language is to use the final specifier. So basically I can say final when I'm defining this class and declaring its base classes, and this prohibits circle from being the base class of any other class. And so basically this is the example of the final specifier used to declare a derived class as final. The second context in which you can use the final specifier is when you're declaring a virtual function in a derived class. So virtual functions are used to, this is a short aside for people who may not be familiar with the concept of virtual functions. So virtual functions are used to implement the language feature called dynamic polymorphism. What this means is that the behavior of an object will depend upon its dynamic or runtime type rather than this declared or static type. So in the example that I showed you earlier, you could have a pointer with a static type of shape, and you could invoke a draw method on it. But if the if your pointer happens to point to an instance of a rectangle object, then it is rectangle's definition of draw which would be called, and if it happens to point to an instance of a circle object, then circle's draw method will be called. So this is what I mean by dynamic polymorphism. The behavior of that function call depends upon the runtime type of the object and not on the declared or static type. And so if you declare as a virtual method in a derived class as final, what you're saying is that a derived class of that class cannot override the final method. So again, if you try to override a virtual function which has been declared as final, the compiler will emit an error and it will fail to compile your program. So again, if you imagine you're a library writer and you've designed a class hierarchy, and you have some class in which, let's say, one function is you don't want users to be able to override its implementation. So what you can do in that case is, if you declared the class itself as final, you would be prohibiting users from deriving from that class itself. But let's say you want to allow users to derive from that class, but you want to prohibit them from overriding a specific virtual function. In that case, you would use the final specifier for those virtual methods alone. So this is the example I showed you previously, where I declared the entire circle class as final. Now, as I said earlier, this declaring a class as final means that you are doing two things. You are preventing anybody from using circle as a base class of another derived class, and the other effect it has is that because of this, all the virtual functions in the circle class can never be overridden because the class cannot be derived from it. That itself prevents the virtual functions from being overridden. But let us say instead you want to allow users to override this class. So you want to allow users to, let us say, define a subclass of circle. I don't know, perhaps an ellipse, or perhaps we could reverse it and say a circle is a special case of an ellipse. But whatever the reason, let's say that you want to allow circle to be used as a base class of some other derived class, but you don't want to allow one specific virtual method to be overridden. In that case, you would declare that particular virtual method as being final. So this is how you would do it. So you would use the final keyword here and then have the method implementation. And so what this is doing is declaring only the draw method to be final. And this means that circle can be the base class of another derived class, but that no derived class of circle can override the draw method. Now, so no derived class can override the draw method. So irrespective of which instance of a derived class an object can have, if you invoke the draw method, it will invoke this implementation of the draw method. Now, again, you can so when would you use the final specifier? Again, as I said before, let's say a good design guideline for C++ is to keep inheritance hierarchies short. So if you implement deep inheritance hierarchies with many layers or levels of inheritance, then the code becomes difficult to understand, as well as it becomes difficult to maintain, debug, etc., or even modify. The hierarchy may have introduced fragile dependencies. So it's better. It's a general guideline to keep to avoid having deep class hierarchies, and the final specifier is one mechanism which allows you to enforce this guideline. You, as a designer of a class hierarchy, can say nobody can make this class hierarchy any deeper by making the class as final. If you want to allow users to derive from certain classes but prohibit them from overriding certain virtual methods, then you would declare those specific virtual methods as final. So this is in general the guideline for using it. And so you will use the final key specifier in order to follow good C++ design object-oriented design practice. In addition, it has the benefit that using the final keyword enables the compiler to generate better code for you. So I just have examples of three small functions which uses objects of this little class hierarchy that I've shown here. Say you have a function foo which takes a parameter of type pointer to shape. At this point, in this function foo, I'm calling the draw method. So this is this usage is what virtual functions were designed to permit. So in other words, the function foo does not know what the exact runtime type of the shape. All it knows that it is an instance of one of the subclasses of shape. So it can go ahead and invoke this draw method, and this will do a virtual function call, which will then need to go through the so-called virtual function table. So at this point, I want to sort of digress a bit and tell you how virtual functions are implemented and how this fact, how the implementation allows the compiler to generate better code if you use the final specifier. So in this case, so in C++, virtual functions are implemented by using a so-called virtual function table. So if you have a class with one or more virtual functions in it, then at every instance of that object will have a so-called virtual function pointer. We'll have a virtual function pointer which will point to a virtual function table. A virtual function table is basically a table of virtual function addresses. So in this case, an object of type rectangle, if I were to draw its sort of representation in memory, it would look something like you would have the base class, you would have right at the beginning, you would have a pointer to a table of functions. In this case, the table will have two entries, one for the draw method and one for the scale method. So here we have this is an instance of a rectangle object. Its data members will follow this virtual function, virtual table pointer. So here you will have the location data member, and then you will have the width and the height. So the very first member, this is specific to our implementation, but it's a common practice. The very first member of an object of type rectangle will have a pointer to a virtual function table, and these in turn will point to the addresses of the specific functions that correspond to those implementations of those virtual functions. So here, imagine that I'm passing an instance of a rectangle object. So in translating this virtual function call, the compiler will have to generate code that fetches the virtual table pointer, then goes there and identifies the first slot as being that of the draw method, and then load the address of the draw method from this location, and then do an indirect call instruction to call that function. Now, so this virtual function call will always result in this lookup at fetch of the address and an indirect call. Suppose you have, for instance, this function bar where you declare the type of the object itself as circle. So in this case, the type of the static type of the variable circle is pointer to object circle, and the dynamic type is also an instance of object circle. Now here, what the compiler can see is that at compile time, it sees that this method, virtual method, is declared as final. So it does not have to go through the process of fetching the virtual function table pointer and then calling indirectly through that. It can directly insert a call to this particular function implementation or definition. And now this is possible in both cases. That is, if I have the draw method as final, the compiler can do this optimization, and in fact VC++ does do this optimization. And if I declare the entire class as final, then that implicitly means that all the virtual functions in that class are also final, and it can still do a direct call. And but in this case, notice that when the compiler is compiling rectangle, this function, it will not in general know that this draw method will always invoke this draw implementation. Why is that? Because you could have, there is no final specifier for rectangle, which means it's not a final class. You can derive from the rectangle class, and you can then have a call to the draw method, which would either invoke the derived class method if it provides an override, or it will invoke this implementation if it does not override. So in general, this function call here will again go through the same mechanism as this function call, which is fetch the virtual function table pointer from the object, and then fetch the address from the virtual function table, and then do an indirect call. So this is the sort of compiler benefit of having of using the final specifier. So not only does the final specifier allow you to enforce good design practices, it also allows the compiler to generate better code for your program, or for your library or your application. So this code is basically the same that I showed on the board earlier. It's the example shape class hierarchy with the shape as the base class, and two derived classes, rectangle and circle. Initially, I'm just going to show you one virtual method and show you what the difference in performance can be between using the final specifier, which, as I said, results in a direct function call, as opposed to not using a final specifier, where you would have to go through the virtual function table mechanism and fetch the actual address of the function which needs to be called. Here is the code. We have a point structure, and then we have a shape, a rectangle one, and circle. I'm sorry I had to use rectangle one because apparently the rectangle name clashes with an identifier in a Windows header, which I needed for doing the timing. So that's why I have this rectangle one here. So the main code is very simple. All I'm doing is creating an instance of a rectangle one object, creating an instance of the circle object, and I'm also doing one more thing to illustrate when the compiler has to use the virtual function table lookup mechanism to do a virtual call. I'm doing that by declaring a variable of pointer to shape, and I'm just assigning. Now remember, this is a base class, so it can hold either a pointer to a rectangle or a circle, and I'm just assigning the circle pointer to shape. And remember, the circle class is the one which I have declared as a final class. So I have a time it function, which basically all it does is call its first argument the number of times specified by the second argument. So basically you have because this is modern C++, I'm using a lambda to encapsulate a call to the draw method through each of these variables, that is shape, rectangle and circle. and I'm just saying, asking it to give me the time for calling this function 1,000,000 times. Let me go ahead and run this demo. I'll first build it. I'll just hit F7 and it said okay, build up to date. So I'm just going to run it. So as I've set a breakpoint so that you can see the output window. The output window is here, and you can see here that the time for 1,000,000 calls through the base pointer is approximately 3 milliseconds, and this variation is, these two numbers are actually supposed to be the same. And the time without the final, the time for the method call without the final is 2.29 milliseconds, whereas if you use the final, then that time drops down to 1.75 milliseconds. Of course, this is just a toy example where the actual implementations of the virtual methods are empty. I did this just in order to illustrate the difference in the call overhead, the call instruction overhead. There's no actual overhead in time spent in executing the function. That should be very small because it's just an empty function. But even then, you will see the difference between the direct call and the usual virtual function call mechanism. So now I'm going to make the circle class not final, but I'm only going to enforce that the draw method be final. And this is how you do it. You put the final method after the function function name and parameter list. You can put the final specifier, and now I'm going to rebuild it, and it builds, and now I'm just going to run it again. And again, here is the output window. You should see that again, just with this change, you still see the same numbers. That is, the time through the base and time without final are approximately 2.3 milliseconds, whereas if you use a final specifier, then the time has dropped down to 1.7 milliseconds. And this, of course, is a very artificial toy example, but I just wanted to show what is the difference in runtime performance of your application through the use of the final specifier. Now I'm going to show you the actual code generated for a virtual function call, one to a method not declared final and the other declared final. As I explained before, one will go through the virtual function table lookup mechanism, and there is runtime overhead associated with this, and the other results in a direct call. So as I've just written a little function called showAsm which takes two parameters, which is the first is a pointer to a rectangle and the second is a pointer to a circle. Remember that it's the circles method, draw method, which has been declared as final. Within the function, all I'm doing is calling the draw method for each of those pointers. And if you look at the assembly code generated for this function, remember the function is called showAsm. And if you look at the assembly code generated for this function, you will see there's not much here. You will see one indirect jump instruction. So what the compiler has done here is it has generated two calls to each of the draw methods, but the second call to the circle draw method was emitted as a direct call. And the compiler, this being a release mode compiler or an LTCG compile, it has inlined the body of the definition, and that body being empty, it has completely optimized it away. And furthermore, this means that this pointer for the second call, for the call from the circle, will be unreferenced, which means the parameter circle itself is unreferenced. So you will see it has now become a dead parameter. This is one of the optimizations that the compiler does during LTCG. So you will see that the circle parameter has now become a dead parameter, and this also means that it will not, the circle parameter will not be passed to the call at the call site itself. That overhead will also be removed. So this the circle parameter is dead and its body has been completely optimized away. all you will see is one indirect, what is supposed to be an indirect call, but even that the compiler has done what is called tail call optimization. This is done when there is a call at the very end of a function, and all that a function does after returning from the call is returning from this function. So what it does is convert the call instruction into a jump, so that when the called function returns, it returns to the caller of show-asm directly, thus avoiding two return instructions. These are the optimizations, and you'll see that those two methods, in case of the rectangle draw method, the compiler could not do anything because the function call is opaque. Being an indirect function call, it is opaque, and you cannot do optimizations such as inlining or any other whole program optimization. Whereas with a direct call, the compiler, it can do inlining, and that itself will enable further optimizations. Plus, it has the benefit of all the other optimizations associated with making a direct call. So this is just a little demo that shows the difference in code between a function call to a virtual function not declared as final and one declared as final. Hope this makes it clear, and this is the performance benefit of using the final specifier. And as I mentioned earlier, there are other design practice benefits from using the specifier as well.
Hey, that was nice. Thanks for doing the video. So
absolutely.
I really like the fact, the control. I really like the things in C++. Was of course well designed by the standard committee. You can control all the class, or go down to the single function if you don't want to finalize or close the entire class. So that was pretty nice.
I think what I like about it, you have the performance speed up by careful utilization of the keyword, and so it's like, in a way it rewards you for having well thought out code, and figuring out what's not supposed to inherit from or be inherited,
and give the information to the compiler about that.
And in return, faster code.
Yeah, and also you're right. There is also the return of, the code is clear because that class is meant not to be, inherited from.
Add
so that's
clarity.
good.
So yeah.
Cool.
So you always ask me,
Right.
what's
What's
next
next?
on GoingNative? So
So
maybe turn the
this
question to you
time
this
me.
time.
So what's next? I don't know. No, it's we try to get some people from the debugger team. Some of my friends there. So we are gonna go and ask them some of the, the trickness, the things that are inside how the debugger works. I always want to know myself. That's why I want to do this episode. So we see if we can pull it off.
Cool.
Next month.
Sounds good.
See you.
Thanks for watching.